Hi, in this video we will introduce the Markov chains through an example. Let us start the example. A small town with population of 300 people has two coffee shops, coffee shop A, coffee shop B. It is known that of those who drink morning coffee in coffee shop A, 40% will come back to A the day after. So only 40% will come back and 60% will go to coffee shop B. And of those who had morning coffee in B will come back for the morning coffee the next day. So 30% of B's customers will come back the day after. Now, the question is, if 200 people had their coffee in coffee shop A at Monday morning, how many will buy their coffee from A on Wednesday? Okay, let's rewrite this information. So I have two coffee shops, A and B. What we know is that if someone gets coffee on a day from A, then by the probability of 40%, which is 0.4, he will get the coffee, she will get the coffee from the same coffee shop A the day after. So this is basically the day after. But the rest will go to the coffee, to the shop B. So 0. With the probability of 0.6, they will go to the coffee shop B the day after. For B, if someone has the coffee by the probability of with the probability of 0.3 or 30%, will come back to B the day after, or they will go to the next coffee shop, which is B. Yeah, so this is the information given there. I just wrote them in a nice way. Okay, now we have Monday. We know that 200 people had their coffee from there. This is coffee A, coffee shop A. Well, we are assuming that everyone is getting coffee, so 100 of them, of the people in the town, will go to coffee shop B. Then on Tuesday, well, we know that we will have two different parts for the customers on Tuesday. One, the ones are returning. So returning guys. So the ones who got coffee Monday from the coffee shop A and from the other coffee shop. And we have to add these guys, yes? What is this? Now, we know that 200 of them had coffee Monday in A, so with the probability of 4% or 40%, they will come back to the coffee shop A again. So 40% or 0.4 of 200 people will come back to the coffee shop A. And while from the customers of coffee shop B, there will be 0.7% which will go to coffee shop A. So that is where we have 0.7 times 100. So these guys, so 0.4 times 200, that will give us 80. And people coming from coffee shop B will give us 70. Together, this is 150 customers will buy coffee Tuesday from coffee shop A. Well, we can do similar computation for coffee shop B. Why don't we go ahead and find coffee shop A? Because we are looking for Wednesday. Let me start this way. So this is Wednesday. So on Wednesday, we know that again 0.4% of the day before, this time is 150. These are returning. And plus 0.7 of the people that who bought coffee on Tuesday from B. So I need this number. What is this number? First, I have to get that and then plug it there. So that's why I need to find B here. So returning people here is that 0. Let me write returning people here. Returning. So 0.3 per 0.3 of the total 100 plus from A, coming from A. How many of them coming from A? Well, we know that 0.6, the probability of 0.6, the customers who bought coffee Monday from A will go to coffee store B. So this will be 0.6 times 200. And this is what? 120 plus 30, which is 150. Now that I have 150, I can plug it in here. And I see that 150 here. This will give us 60 plus... the first one is 60. The second one is 7 times 15. That is 105. And all together will be 175. What will happen here? Well, you can do the similar computation, but in this case, we know that the sum of the customers always add up to 300s. Yes. But if you want to do, they add up to 300. So this will be 125. So in other words, if you want to do the computation, this will be 0.6 times 150 plus 0.3 times 150. That will give us that number. Very nice. So this way we found what will be the number of customers on Wednesday in coffee shop A. Well, if you look a little bit carefully, closely, you see that the numbers we found up there, it is like we are multiplying vector 0 or matrix 0.4 and 0.7 to the vector 200, 100. You see the first row, first column is exactly these numbers. And for the second row, you have 0.6, 0.3. And this way, basically, if we started with the vector 200, 100, we get the customers in the second day by multiplying this matrix to 200, 100, which is 150, 150. And then for the third one, we do exactly same thing again, 0.4, 0.7, 0.6, 0.3 times 150, 150, which gave us the numbers are here, 175, 125. So as you see, we have a process which evolves as time proceeds. And at each time, while A and B are different states. So at A, we mean coffee shop A, coffee shop B, you get different numbers. And as we move on, or the system evolves, some of the people in state A will go to state B, and some people from state B go to state A. We put all these states together and we form what is called a state vector. And at the first day, well, the 0th day, this is the 1. And what we found here is that on this, after the first day passes on, the first step is taken, we get the state vector x2 and then x1 and then x2. But we saw that there's a good relation between x1 and x0. x1 is obtained by multiplying this matrix, let me call it P, times x0. This is x0 vector and that's P. And this guy here, this is P, matrix P times x1, vector x1, that is x2. And this can continue forever, yes? So this is as an example of a Markov chain. What is a Markov chain? Well, first of all, it is a process which evolves during the time. So it is an evolving process whose states can form a state vector at step k, we denote it by xk. Okay, so we have x0, x1, x2, x3, and so on. And the way it changes the states, each component of vector state, so the values of the states at next step depends only on the values of the previous or the present step. So the next step always depends only on the values of this step, present step, not on the values of the states on the previous step, not on the previous steps. And the way states transition from one to other is fixed, and we assume that the transition probabilities from a state to another stays the same. Well, putting all these together, we have a state vector x1, x0, x1, x2, and so on. And we know that x1 is given by a matrix called transition matrix times x0. And x2 depends on the values, only depends on the values of x1, a step before that, and we get that state by multiplying the matrix P, transition matrix P, to x1, and x3 is equal to P x2, and so on. And while here P is called the transition probability, transition matrix, and we know that it contains the information or the probabilities. The ij component of the transition matrix P is equal to the probability of going from state J to state I in one transition. So it is equal to probability of going from state I to state J. In other words, when you have the matrix P, you consider these guys to be the present states. So the first state, second state, up to, I don't know, n state. And then you write the probability of transition from the first to the first state in the next step by 1. So P11 would go there, P21 would go there, and P N1, and so on. So you put the probabilities as going from column to rows, and put all of them, form the transition matrix, and then use it to find different steps. Well, and it is easy to see that remark, since every state turns in one of the given states, so the probability of transitioning from state 1 to state 1, 2, 3, add all of them, they should add up to 1. The numbers, the entries of the transition matrix are all non-negative. Let me write it, non-negative numbers. They can be 0, but they cannot be negative numbers. And sum of the entries of each column is equal to 1. So if you add entries in a column, they will add up to 1. You can see this in our example. Let me just quickly go back. In our example, the transition matrix is 0.4, 0.6, 0.7, 0.3. And as you can see, all the entries are positive. As I said, it can be 0, but in this example, they weren't. And when you add the entries on in the column, you get 1. All the columns are so-called probability vectors. Okay, so we will go back to this and do more examples and see what other topics we can cover here.